Hello, this is Professor Merrill Lichty. In this video, we're going to look at a two-sample t-test, which is used to compare two unknown population means. So far, we've been talking about one-sample procedures, where we're interested in the population value or characteristic of a single population, and this requires us to take a sample from that population. A simple extension of that, which is also something that's very common in statistics, is when we want to extend it to two different populations. If we want to know what's the difference between the mean for two populations, well, in order to do that, we're going to have to take a sample from each population, and we call that a two-sample test. We have to consider the value of the standard deviations, and just like we did with the one-sample procedures, typically standard deviation is not going to be known, and so we're going to have a t-test. Here's a typical example for a question like this. Drexel Nova University has an MBA program, and they admit all sorts of different students. A researcher has decided that all undergraduate majors can be classified as either technical or non-technical. So technical would be things like math and engineering, science. Non-technical would be English, art, political science, and so forth. And the investigator is interested in whether there's a difference long-term in the career success of the MBA students based on this category. So they're going to look at the salary, gross salary, 15 years after graduation, and use that as a measure of success. Here's the setup. The null hypothesis says that the average salary 15 years out for the tech group is the same as for the non-tech group. The alternative says that those average salaries are not the same. This coincides with what the researcher was initially interested in because they didn't have a feeling one way or another as to which would be higher. In situations like this, it's very common to subtract the one mean from another. In other words, take the difference in the means. So the null hypothesis says the difference is 0, and the alternative says that the difference is not 0. So we're putting the burden of proof on showing that there is a difference. Otherwise, we'll go with the null hypothesis and conclude that there is no difference. So let's look at some data now. We've got two samples, one for MBAs with a technical background and a sample average of 135.2 and a sample standard deviation of $28,000. Again, this is 15 years out from graduation. The second sample comes from MBAs with non-technical backgrounds, and they have a sample mean of 151.3 with a sample standard deviation of $36,000. So the question we have is whether this data provides evidence that there really is a difference in the mean. If you look at just the sample values for the means, we see 135.2 versus 151.3, and it's clear that the sample mean for the non-technical background students is higher than for the technical students. And the question that we have to ask ourselves is that difference due to randomness or just chance, or is it due to the fact that the alternative hypothesis is true? And that's what we're trying to get at. Turns out there's two versions of the t-test for this situation. First one's called the pooled variance two-sample t-test, or just the pooled t-test. And the idea here is that even though the population variances are unknown, we assume that they're equal to each other. And since they're equal to each other, we're going to use both of the sample variances and pool those together to come up with an estimate for the population standard deviation or variance. The second variation of this test is called the separate variances t-test, and it doesn't make that assumption. It doesn't matter which one we're using, we still have to have x1 bar and x2 bar be normally distributed. And we know how that can happen. Either we have large sample sizes, at least 30 for both samples, or the populations we're sampling from are both normal. So let's look at the mechanics for the two-sample pooled variance version of this test. And the first thing we need to do is get an estimate for sigma squared, the population variance. And since we assume that the population variance is equal for both populations, all we're going to do is combine the estimates that we have for the variance for both of the populations together in this fashion. So we call the pooled variance S sub p squared, and all we're doing is taking a weighted average of the sample variances, where the weights are what we call degrees of freedom. Once we have the pooled variance, we can calculate a t-statistic, and we do that using this formula, x1 bar minus x2 bar minus the difference, the hypothesized difference in the means, and then we're going to divide that by the square root of S sub p squared times 1 over n1 plus 1 over n2. Now typically d0 is going to be 0 if we think that the population means are equal to each other, and that kind of goes along with the idea of the null hypothesis. Null means no difference, but sometimes you might want to put in a non-zero difference for d0, and that certainly is fine to do. The last thing we need is degrees of freedom, which are going to be n1 plus n2 minus 2. Now, where this formula comes from, I'll refer you back to the text or the notes, but it really does take the same form as the standardized z test statistic or the one sample t statistic, in that we have x1 bar minus x2 bar. Think of that as a single value. We're subtracting from that some hypothesized mean, and then we're simply dividing by the standard deviation of x1 bar minus x2 bar. Okay, so let's look at the details here. We have n1 is 40, n2 is 50. Add those together, subtract 2, that gives us degrees of freedom of 88. And we have a t-distribution then on 88 degrees of freedom. We know we have a two-tailed alternative hypothesis, and alpha is 5%. So that means that we're looking for the upper 2.5% and the lower 2.5% region in a t-distribution with 88 degrees of freedom. Minitab will tell us what the critical values are for free, negative 1.99 and 1.99. This means that we're going to reject the null hypothesis if our t-statistic is bigger than 1.99 or smaller than negative 1.99. At this point, this should start sounding very familiar, because this is really the same thing we did with the one sample procedures. Just what's different, the details are a little bit different. Different degrees of freedom, different test statistic, but the idea is the same. You could look up the values that we have reported here in a t-table if you like, although you will find it difficult to find one that has 88 degrees of freedom. One alternative that is often recommended is just to use the normal table, especially as the degrees of freedom get large. And that's because as the degrees of freedom do increase, the t-distribution gets closer and closer to the normal distribution. So you could use negative 1.96 and 1.96 if you like, but if you have software, it's better to keep things as accurate as possible, so we'll use 1.99 and negative 1.99. Okay, so let's just plug the numbers in, get our pooled variance, which is going to be n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared divided by n1 plus n2 divided by 2. Just plug those numbers in and we get 1069.09. If we take the square root of that, we get the pooled standard deviation of 32.697. And at this point, we should probably do a check. This pooled standard deviation is supposed to be a weighted average, or at least the square root of a weighted average. It should be between the sample values of 28 and 36. And it looks like it is 32.69. So now we're just going to plug all of those numbers in to get our test statistic, and our t-value then is negative 2.32. And that's going to be the number that we compare with our critical values, and we'll do that in just a minute. Of course, there's an easier way to do this, and that is to use software. And here is the Minitab interface. If you go Stat, Basic Stats, and then sample T, you can plug in the numbers. In this case, we've got summarized data, so we'll just put in the sample sizes for the first and the second population, sample mean, sample standard deviation for both of those. And again, remember we're using the assumption of equal variances, so make sure you check that box. And then it's also good to look at the options and make sure that we got the confidence level correct, 95%. That corresponds to alpha being 5%. The difference in the hypothesized values is going to be 0, and the test statistic is, the hypothesis, the alternative hypothesis is a two-tailed, so we want to make sure that we have not equal in the alternative box. Click OK twice, and here is the output that we get from Minitab. First of all, there's a summary of the data that we put in, and we see that the difference that we're looking at is mu1 versus mu2. That's just a restatement of the null hypothesis. The estimated difference is negative 16.1. We get a 95% confidence interval for the difference. We'll talk about that in a little bit. The test statistic of the difference is going to be negative 2.32. That's the same thing as what we calculated by hand. A p-value is actually given to us for this as well. That's one feature that you get when you use software. And degrees of freedom are given to us, and then the pooled standard deviation of 32.697 is also given. So what do we need to compare with our rejection region? Well, the t-value here of negative 2.32. That's less than negative 1.99, so that does say that there is evidence that the difference between salaries for tech versus non-tech people is significant, and it looks like it's favoring the non-tech background, and we can see that same result by looking at this p-value that's given to us again for free. Since the p-value is less than 5%, which is our alpha level, that means p-value is low, H0 must go. We saw the confidence interval for the difference in the means in the last slide. And what does this mean? Well, we have 95% confidence interval for the difference, and that is between negative 29.88 and negative 2.32. So there's a couple of things this tells me. First of all, we're going to reject H0 because the hypothesized value of 0 is not in that interval, and so that means that the conclusion would be that there is a difference between techie and non-techie backgrounds. The second thing we get is an estimate for what that difference is, and based on the data that we have, which is not a lot of data, we see that the difference is somewhere between $2.3 thousand and almost $30,000. So good news for the non-techies. But the point here is that we have the same story as told by the p-value and the critical value approach. So let's finish off this video by just noting that the assumption of equal variances is sometimes not one that you can make, and if you're in doubt about whether you should do that or not, then you can simply uncheck the assume equal variances box and do the unequal variances t-test. And we'll talk later in class about how to actually test for that. There's another hypothesis test for that. And if it just so happens that you know what those variances are, then there turns out to be a two-sample version of the z-test. And Minitab will do both of those. If you want the details on those, I'm going to refer you to the text.